Is there a way to represent pi not from a circle, but as a limit or something? Apparently there are ways to represent pi as an infinite series, as integrals, as limits, but it's not quite clear why those representations the way they are. I mean, look at that. But I can tell you where one of those representations comes from. The general idea behind this formula goes like this. If we'll start inscribing regular polygons into the circle and we'll increase the number of edges in those polygons, then perimeters of those polygons will start approaching the circumference, which we know is pi. But honestly, in my case, I didn't think about the formula right off the bat, because I just started to calculate perimeters of regular polygons that are inscribed into the circle, and then turned out that this formula takes place here. So let's actually start computing some perimeters of regular polygons. First off, let's look at the square that is inscribed into the circle. We'll always look at the circles with the diameter that is equal to 1, because those circles have the circumference that is equal to pi, which is what we need. So after labeling some vertices as A, O, and B, we can see that AO is the radius of the circle, and the BO is also a radius of that circle. But we know that the diameter of that circle is 1. That means each of those segments are 1/2. Well, we can use the Pythagorean theorem to find AB. The segment has the length square root of 2 over 2. So in order to find the perimeter of the square, we have to multiply that side by 4, because the square has 4 same sides. So quick note, we have a infinite sequence of polygons, and the number of their sides is, let's say it's n. It's increasing to the infinity, but we don't have to actually look at every single n. So in order to make our life easier, we will look only at those n that have the form of 2 to the power of something integer, of course. That's why after a square we will be looking at octagon, and after that we would have to look at the 16-side polygon. So let's look at the regular octagon that is inscribed into the circle with the diameter 1. This time, in order to find the perimeter of this octagon, we would have to multiply 8 by the length of one of the sides of that octagon. Let's name it AB. So the perimeter of the octagon will be 8AB. To compute AB, let's draw some more lines. We can find out that the angle AOB is equals to 45 degrees because the angle BOC is 90 degrees, and OA divides that angle into the 2 equal parts. We also remember that OA and OB both equal to 1/2, because OA is a radius and OB is a radius. Now to find AB, we can use the cosine law. Which finally gets us, as a result, a length of AB equals to square root of 2 minus square root of 2 divided by 2. But remember, we have to multiply that value by 8 to get the perimeter of octagon. So the final answer is 4 square roots of 2 minus square root of 2. I want to remind you that we're trying to prove this formula, and the perimeters of polygons should look somewhat like it. And if for square it doesn't quite look like it, for octagon it's already much more similar to this formula. But now we will try to look at the general case where n equals to 2 to the power of k, where k is some integer. So let's assume we have a regular n-sided polygon that is inscribed into the circle with diameter 1. If we draw all the diagonals of that polygon, it will be splitted into n equal triangles. So let's look at one of those triangles. Let's call it A, B, and O. And it's not difficult to see that to find the perimeter of that n-sided polygon, we would need to multiply n by AB. But how do we find the length of AB? To find AB, let's first draw OH. That is going to be perpendicular to AB. Since those two angles are equal, we can definitely say that the angle AOH equals to 180 degrees divided by n. Let's call it alpha. Now let's look at the triangle OHA. Since the angle OHA equals 90 degrees, we can say that sinus alpha equals AH divided by OA. But OA equals 1/2 because it's a radius of our circle. Thus, we get sinus alpha equals 2AH. But we also can notice that AH and BH are equal segments. So AB is exactly 2AH. And AH, 2AH, is exactly sinus alpha. All of that allows us to state that perimeter of our n-sided regular polygon equals n times sinus 180 degrees divided by n. So the only one thing left to do now is to find sine of that angle. But let's not forget that n is 2 to the power of k. That means we can rewrite it as 2 to the power of k sine 180 degrees divided by 2 to the power of k. So let's try to find this sine. First of all, let's rewrite it as square root of 1 minus cosine squared of the same angle. We can do so because there is this rule in trigonometry, and thus we can prove that sine of any angle is square root of 1 minus cosine squared of the same alpha. Okay, but how do we find cosine squared of 180 degrees divided by 2 to the power of k? That's a good question, and we are going to go about it this way. Cosine of 2 alpha is the same thing as 2 cosines squared of alpha minus 1. If we will modify this equation, we will get that cosine squared alpha is the same thing as cosine 2 alpha plus 1 divided by 2. And therefore cosine alpha is square root of cosine of doubled alpha plus 1 divided by 2. Now if we will look closely, we will notice that each time k increases by 1, this angle gets 2 times smaller. Because 2 to the power of k plus 1 is the same as 2 multiplied by 2 to the power of k. So each step we make the angle 2 times smaller. And in this formula we can see that in order to find new cosine, we just need to use our previous cosine and put it inside this expression, because 2 alpha is also 2 times bigger than alpha. So let's start by looking at the case where k equals 2. Cosine of this angle will be just cosine of 45 degrees, which, as we know, just square root of 2 divided by 2. Now let's look at the k equal 3. To find new cosine of this angle, we can just use this formula here. and say that it's the square root of previous cosine plus 1 divided by 2, which is, if you simplify this expression, just square root of 2 plus square root of 2 divided by 2. Okay, we find cosine of that angle, but sine of that angle can be found using this formula right here. So if we'll put everything we know to that formula, we'll get something like this. And when simplified, it will look like 2 minus square root of 2 divided by 4. That means 2 minus square root of 2 divided by 2. And we just proved that perimeter of regular octagon is, as we saw before, exactly 4 times square root of 2 minus square root of 2. But this time, we did it via those formulas. Okay, we're now ready to prove that cosine of 180 degrees divided by 2 to the power of k is exactly square root of 2 plus square root of 2 plus and so on plus square root of 2 divided by 2, where the number of 2's here is exactly k minus 1. How are we gonna do this? Well, by induction. Let's first note that cosine of 180 degrees by 2 to the power of 2 is square root of 2 divided by 2. That's pretty simple. Then we're going to assume that this is true for some k, and we'll prove it for k plus 1. So cosine of 180 degrees divided by 2 to the power of k plus 1 is the same as square root of, let's remember this formula. So it's the same as cosine of 180 degrees divided by 2 to the power of k plus 1 divided by 2. Here we are using our assumption and rewrite the whole thing as this gigantic expression 2 plus... Remember here they're exactly k minus 1 square roots plus 1 divided by 2. If we'll simplify it further, we'll get exactly this formula, because square root of 2 plus square root of 2 plus so and so on, square root of 2, and here is already k times divided by 2, which is exactly what we need. It's 2 plus square root of 2 plus and so on plus square root of 2 divided by 4, but it's a square of 2, so we can say that it's just 2. Okay, we proved this formula. So if we will put this expression right here into this formula, we'll get something like 2 plus square root of 2 plus square root of and so on plus square root of 2 divided by 4. Remember, cosine here is squared. So when simplified, it will take this form. 2 minus, so remember, this is the only minus in the whole expression here. 2 plus square root of 2 plus and so on plus square root of 2 divided by 4, which is simply 2 square root of 2 minus square root of 2 plus and so on plus square root of 2, where there are exactly k minus 1 square roots. Now let's see what we get as a perimeter. We will get exactly 2 to the power of k multiplied by this whole thing, 2 minus square root of 2 plus so on and so forth, square root of 2 divided by 2. So this thing can be put right here into the power, and the final answer is 2 to the power of k minus 1 multiplied by square root of 2 minus square root of 2 plus square root of 2 plus and so on plus square root of 2. Ta-da! There are only k minus 1 square roots. Great! As you can see, we indeed get the formula that we started with. But it's not obvious how to come up with formula like that. You can just sometimes make an observation that leads to some kind of interesting result. So I hope it was some kind of interesting for you to watch. If so, make sure to subscribe and leave a like.